and welcome to this is the final stretch of instructional aspects of classical. So what we're going to be covering in this session now is looking at the estimation of completeness of death registration, and we're going to be doing this in three parts. We're going to be looking at using the UN World Population Prospect as the denominator for all deaths, infant deaths, 5 deaths, using alternative estimates for the denominator from sources from other estimates of the true number of events, the true deaths which are occurring. And then to wrap up, I want to give you a very high-level introduction and overview to what are called the death distribution methods demographic analysis that can be used to estimate the completeness of adult death registration. And that is a completely different way of thinking about different approach to estimating demographic techniques. So when we're talking about estimating completeness of death registration, many of the same considerations and approaches apply to the routine estimation of death registration as we've already described for the estimation of completeness of birth registration. We need to still ensure that the numerator is properly constructed, exactly the same way as we did birth registration, so that if our significant delayed registrations of death, those are accounted for analysis that incurred but not reported type framework, both 0 and ultimate levels of completeness estimates. We need to understand the limitations again as before, and caveats associated with what denominator you choose to use to compare those events with the vital registration system data. And again, to re-emphasize that in all of these exercises, that local expert input as to the sensibility of the denominator deployed and interpretation of the result is always going to be required. So with only very minor adjustments, the standard approach is center on using the UN World Population Prospects, the UNWPP data, as the denominator for the estimation of deaths, infant deaths, and under 5 deaths. And we'll be talking a little bit about those alternative estimates of the denominator as well. But as I've just mentioned on the previous slide, there are approaches so it would be broadly grouped or described as indirect demographic techniques that can be used to estimate the completeness of death reported for adults. And I'm going to give some introduction to that as well. So when we're thinking about death registration relative to birth registration, there are some important conceptual differences. Firstly, and this does bear mentioning, that problem which we encounter with birth registration often being delayed by many, many years. Commonly encountered reason for that being that often births are only registered when the child needs to go to school. Those problems do not necessarily pertain with delayed registration of deaths, because there isn't that same kind of reason that might drive very late registration of births. But at the same time, the deaths in the population are perhaps a little more intricate than the births and the still registration data on births in a particular population. This is for several reasons. The first is that deaths occur at all ages, and that's trite and it's not obvious state, but let's think about it here. Might neglect to take that into account. And we know that registration completeness may vary by age. Okay, so that there might be particular ages at which the completeness of registration might be very different from that at other ages. There may be very strong sex-specific aspects to the ages at which deaths occur, and perhaps whether those deaths are registered. So routinely what we find, for example, is that deaths of very young children are often not notified to the authority shape or form. There you don't have a problem necessarily of late registry of infant child deaths, but you might have a problem of non-registration of infant child deaths. And so where possible, one should be aiming always to try and assess particularly the completeness of infant and child death registration, in addition to overall measures of completeness, taking the total number of deaths in your population relative to what you'd expect, and that would be your measure of completeness. But if we know or suspect that there are strong age gradients in the completeness of that registration by age or by certain categories of sex or their young children under 5, we really want to be able to try and get a handle on that as well. So we want to understand death registration, not only in its aggregate form as we do with births, but we also might want to do it for certain segments of the population to try and get a handle as to where there might be particular problems with the reporting of child death. This is often the case. I mean, take my own country, for example, in South Africa. A death of a child can only be formally registered on our national population register. Birth had already prior been registered. So a birth which has not been registered is not readily and accessibly entered into our civil registration license system unless there's a corresponding birth record against which to match those that death. And so in situations where the child's birth has not been registered, quite often the case is the death will not be registered either, and that is going to create particular problems quality of the death registration of children. When we are using data from the UNWPP, the same general approach for estimating birth registration relative to the UNWPP can be applied with limited modification. But we are limited by what is publicly available, the output from the UNWPP on an annual calendar year basis. In general, the UNWPP projects the population in 5-year age groups over 5-year period, 5 calendar year periods. And they only produce limited tabulation of the annual number of events on a single calendar year basis. What is produced and made publicly available by the UNWPP is firstly that there's all age deaths classified by sex, so that's the deaths at all ages for males and females separately. For infants, total under the age of 1, and then also we're able to derive some estimate of children under the age of 5. So could I excuse me a second? I've got someone to Hi, sorry, apologies for that. I had to step away from my desk for a minute. There was someone at the door delivering a parcel. I am truly apologetic. So the data from the UNWPP, which are publicly available on a calendar year basis, only include the deaths to all ages for males and females separately and for the total population. For infant deaths of both sexes combined, so we cannot analyze from the UNWPP the infant deaths of males and females, and there's no direct way in which we can separate out the infant deaths by sex from those data. And I've put in parentheses that one can also just about, but not entirely, derive some estimates of the number of children under the age of 5 on an annual basis. But that is also not by able to be disaggregated by sex. I put the under 5 mortality, the deaths of children under the age of 5 in parentheses there on that slide, because there's I have to offer a specific caution as to how one works with the estimate of completeness of under 5 mortality from the UNWPP data. And this is because while the UNWPP publishes estimates of the numbers of infant deaths, which is obviously what we want to have as our comparator, as our denominator, when working with trying to derive estimates of completeness. The UNWPP publishes estimates of the numbers of infant deaths, and so it can be used directly. But that is not the case for under 5 deaths. And so therefore, if you are producing an estimate of under 5 completeness, or the deaths of children under the age of 5 and the completeness of those registrations, you do need to exercise a greater degree of caution and circumspection in using that metric and interpreting the measure of completeness of under 5 mortality. In the spreadsheet, which is available to you, the number of deaths under the age of 5 is an approximation to what we think might really be implied by the UNWPP data. We produce it as part of the spreadsheet because we think it is an important metric which you should be wanting to look at. And so even though it's not a direct output from the UNWPP, we think that it is appropriate to at least offer some mechanism to assess the completeness of under 5 mortality. Now, because there's not sufficient data available from the UNWPP to calculate this with any great degree of precision, the way it has been implemented is that the number of deaths under the age of 5 is approximated by applying what the UNWPP does publish, which is an annual estimate of Q5. Q5 in demographic terms is the probability of a child dying before the age of 5 in that population in a given calendar year. And we apply that metric of the Q5 to the number of births 2 years previously. And the reason for that is because we know that under 5 mortality is very heavily concentrated in the first couple of years of life. And so therefore, the mortality under the age of 5 is largely going to be driven by mortality in the first 2 years of life. And so we apply those estimates of Q5, the probability of dying between birth and age 5, to the number of births published by the UNWPP for the year 2 years before the estimate of the Q5. Investigations as to whether this is a reasonable approximation show that it is reasonably robust, but is less so when either the annual number of births or the annual estimate of Q5 is changing rapidly. In most countries in the world now, certainly for the current periods, the 2010 onwards, that is less of a problem than it might have been with data from the 1990s, for example, where in a lot of countries which were undergoing very rapid fertility declines, the number of births or the estimate of Q5 might have been changing far more rapidly. But in most situations, a comparison would seem to suggest that the approximation is robust and at least will provide some kind of peg in the ground against which to estimate under 5 mortality. So sorry, let me just put this up here. So on the resources Excel spreadsheet, which is available to you, under the UNWPP data, what we have here is we have the ability to select what measures of completeness you might want to derive relative to the UNWPP data. You can take deaths at all ages for both sexes, so that's the total number of deaths in the country, deaths of males and deaths of females. That might be important for a number of reasons, not least of all for inequality assessments. You might want to be able to investigate the number of infant deaths, as deaths under the age of 1 for both sexes, or the number of child deaths under the age of 5 for both sexes. And so you do have an option for 5 possible investigations into death registration completeness, which are either based directly on the UNWPP data, or in the case of the child deaths under 5, that's approximation to what we think are the number of deaths under the age of 5 in that population. But I must caution again that when using that last metric, the child deaths under 5 for both sexes, that you must be alert to the fact that those estimates are not derived directly from the UN, or not sourced directly from the UNWPP data, but are the result of a further assumption about the information. In the data, which is from the UNWPP here, this is make it a little bit bigger, you'll see that the information has been placed into the spreadsheet for all those 5 categories. So you don't need to go and find the UNWPP data, the total number of deaths, the male and the female deaths, which will sum to the total number of deaths, the number of infant deaths, and the under 5 deaths, which I've put a little flag there, is not entirely sourced from the UNWPP data, but is an approximation to what we think might be the case in those data. But beyond that, there's no real difference in using the UNWPP data for death relative to the estimation of completeness for births. One would still go through this process of extracting from your data the input data of the incurred but not reported events, and one would then use exactly the same approach as we had before to derive our estimates of completeness. And exactly as with the births, the deaths will be populated from the UNWPP estimates. You could place your own estimates in there if you had an alternative set of estimates, and the process is essentially the same. I do note, and I said it right at the start, that in general, in this matrix of your input data classified by year of occurrence and the lag to registration, that we tend to find that very late registration of deaths is much less of a problem than the late registration of births. And so you'll expect to find a far lesser discrepancy between what we'd call a year 0 estimate of completeness and a ultimate level of completeness than you would expect to find with your registration of your birth data. But what I did point out, though, is that you're more likely, however, to have simple, straightforward non-reporting or non-registration of deaths, and those might be particularly at younger ages, which is why, if at all possible, you should be able to, you should try at least to estimate the completeness of infant deaths and under 5 deaths as a routine exercise, and compare that with your overall estimates of the completeness of deaths, say for both sexes. Obviously, if your estimate of infant completeness comes out to be relatively low, or quite a lot lower than your overall estimate of completeness, that would imply that your completeness of your deaths at ages other than the infants is more complete than it is amongst the infants, and that's going to be then affected by the relative balance of your infant and other age deaths. But other than that, there's no particular complexity associated with using the UNWPP data to estimate death registration completeness, and exactly the same approaches can be adopted. As I say, you could use a different numerator for whatever data you have available to you there. You might want to do it for only a certain age range, or for a certain sex, or for a certain region or a province, and all that you would require then is an estimate of what that denominator might be for that particular subsection of the population you're looking at, by age, by sex, by region, or anything else you're interested in working with. So the UNWPP data are not particularly complicated in terms of estimating death, but except for the fact that you are recommended to try and do the assessment of infant and child deaths separately, as a very important check as to the functioning of your CRVS system. When one's talking about using alternative denominators for estimating completeness of death registration, exactly the same considerations which were mentioned when discussing alternative denominators for estimating completeness of birth registration apply. And so we're just going to quickly step through those again to make sure that you're reminded of the kinds of concerns and which we might have about data from other sources, and the kind of questions which you should be asking about these sources. And we ask particularly whether the annual estimates of death are consistent and plausible. Do they concur with other estimates? If you have estimates from the UNWPP, are they consistent? You need to try and understand the assumptions, models, methods used in the derivation of the number of the deaths, and need to again ensure that if you are using estimates from another source, that those are not drawn directly and unmodified from the CRVS system. If you're working with data for a subpopulation, in this case by age, by sex, by region, you need to ask how those estimates were derived. Particularly because of the limitations of the UNWPP data, you might well often be forced back into using output, say, from Spectrum, the population projection software, which is used by a great many countries in the world, where you might be able to extract the exact projected numbers or estimated numbers of deaths, say by province or by or in certain age groups, or by sex, which you can't get from the UNWPP. And so you do need to just make sure that if you're working with data for a subpopulation, to ask yourself how those estimates were derived. You need to always ensure that the time definitions of the denominator refer to the same time definitions as the numerator. It's not always the case, for example, in Spectrum, that the year of the projection, which Spectrum works with, is exactly the same as the year of the projection, or the calendar year from which you're extracting data from your CRVS. And so you need to ask yourself and check, exactly what is the definition of a year in any alternative data source. It might be that the year refers to the year ending on a 1st of January. It might be the year starting on the 1st of January, or in some cases, it might be a year starting on the 1st of June, 1st of July and going to the 30th of June the following year. And so you do need to ask yourself the question about the temporal definitions of those denominators. And far more than the case with births, which we think are only affected by COVID-19 to a much lesser extent. In your denominator, what accommodation, if any, has been made for the effects of COVID-19 and the deaths arising from the pandemic in the derivation of those estimates of the number of deaths. But all that said, and I did say this on Tuesday, and that the estimation completeness of death can basically follow the same kinds of investigations and same approaches as we did with the UNWPP data on births, which is why one spends, we've spent quite substantially less time on death registration here, except for flagging the particular concerns about infant and child deaths and possibly sex-specific completeness of registration. What I want to do, though, in the final portion of this training workshop is to expose and alert you to what is a really and quite radically different approach to estimating completeness. And these are what we would call the death distribution methods. Now, as an overview, those death distribution methods are a class of indirect estimation techniques. There are 4 or 5 different approaches of using, which will all be grouped together as or labeled as death distribution methods. And the primary purpose of those death distribution methods is not to estimate the completeness of vital registration or census data. It is to estimate the level of and pattern of adult mortality, usually above age 15, using information about the age structure of the population and building a synthetic cohort between 2 censuses. When we talk about a synthetic cohort, what that means is they've got 2 censuses conducted exactly 10 years apart, for example. The people who are aged between 10 and 14 at your first census would now be aged 20 to 24 at the time of the second census 10 years later. And we can look at the change in the age structure of that population and say, well, that reveals something to us about the extent of the population change over the last 10 years amongst the people who were 10 to 14 10 years ago, who are now 20 to 24 10 years later. And those numbers must be able to be explained by an accounting equation that the numbers of people who are 20 to 24 now must be the numbers of people 10 to 14 10 years ago, subtracting off the deaths of those people who died in that cohort over the 10-year period, and adding in any migrants over that period in that age band. And so even though we're not actually following individuals over a 10-year period, as a collective, they represent a cohort of people, and we use that information about the age structure of the population to build those synthetic cohorts. And if we can then bring in that information, not only about the migration, which you'd expect in that cohort, or you've got some other estimate of migration in that cohort, we can then work out effectively what the deaths in that cohort must have been and compare that with what we have about information of the deaths that have occurred between the 2 censuses. And that information will then tell us about the completeness of the information about the deaths between the 2 censuses, about those intercensal deaths. Now, crucially, in the application of death distribution methods, there are 2 sources of information about the number of intercensal deaths. The first is what we'd call a household deaths module, which is routinely asked in many countries' censuses. And that household death module asks respondents from each household how many people in their household died in the year before the census, and what were their characteristics? Were they male? Were they female? Did they die from maternal mortality causes, etc. But for our purposes, the information about the deaths in the intercensal period, which we're going to use to try and estimate our completeness, can also come from the deaths registered in a civil registration and vital statistics system, registered in that system between the 2 censuses. And if we use that information with our synthetic cohorts, which we can say, well, if we've allowed for some migration, which we've estimated, and we have some estimates of the deaths registered in the CRVS system, we can effectively compare the deaths implied by the synthetic cohorts with the deaths from the CRVS system. And that will provide us with an estimate of the completeness, certainly of adult mortality registration in the CRVS. Now, the application of these death distribution methods has been something of some debate. As I say, there are two broad groups of methods, each of which is then further split into two themselves. There are four major methods of these distribution methods. But over time, demographers who specialize in working with adult mortality estimation in developing countries have largely converged on the recommendation that what should be done is that two of those death distribution methods should be used sequentially to estimate both adult mortality and the completeness of adult mortality registration. And what is recommended is firstly to apply one of the methods, which is called the generalized gross balance or GGB method, which for this purpose of the exercise will provide an estimate of the relative coverage of the two censuses. You can imagine that if you've got two censuses at two different points in time, the coverage, the proportion of the population actually covered by those censuses might not be the same. And so the first of the death distribution methods allows us to explicitly provide an estimate of the relative coverage of one census relative to another. What proportion of the population is covered in one census relative to the proportion of the population covered in a second census, the first relative to the second, or the second relative to the first. And the estimate of that relative coverage, which is produced by the generalized growth balance or the GGB method, can then be used as an input into a second method of a second one of the death distribution methods, which is called the synthetic extinct generations method. And so combined, these are now often referred to as the GGB plus SEG method. Okay, so you use one method firstly to get an estimate of the relative coverage, and then you use the second method to actually produce your estimates of adult mortality and your and the completeness of adult registration. In order to apply the methods, the methods or the combination of the GGB plus SEG requires only fairly simple tabulations of data. Firstly, it requires, on a sex-specific basis, the number of women or men in 5-year age groups through to some open age interval, which we call A+, which we would want to be as high as possible, say age 85 plus. So as high as possible, meaning that until you start getting really, really small numbers in that last open age interval. And we'd require the number of women or men in those 5-year age groups and up to that open age interval from two censuses, which don't necessarily have to be exactly 10 years apart. They can be any number of years apart, as I'll show you in a worked example just now. We would also need the number of deaths of women or men, because we're doing this on a sex-specific basis, over that intercensual period, classified by the same age groups as our census enumerations. So in the same 5-year age groups and up to the same open age interval in our data. Now, the two methods are coupled together here to provide both the estimates of mortality, but for our purposes, that's less important than the estimates of coverage, which they are able to produce. The methods do assume that the coverage of the two censuses is the same at all ages. In other words, there's not differential under enumeration by age in one census, or differential under enumeration by age in the second census. And that is usually resolved in many instances by the census agency conducting what we call a post-enumeration survey, which is a survey done immediately after the census has been conducted on a capture-recapture basis to evaluate the coverage of each census, and often that post-enumeration survey is then used to adjust the census results to ensure that it is as good a reflection on the enumeration of the population from each of those censuses. So where a census has been adjusted by a post-enumeration survey, which would normally accommodate for differential age enumeration, and differential age coverage in those censuses, that is often resolved by means of the PES, the post-enumeration survey. We also assume that, or the methods assume, that the completeness of reporting of deaths is constant with respect to age above some, what I put in brackets, relatively young age. In other words, from, say, age 15 and older, for example, we assume that we have to assume that the completeness of reporting of deaths is constant. In other words, that if there's completeness of reporting of 95% at age 45, there's also completeness of reporting of 95% of 95% at, say, age 75. And usually that is not an unrealistic assumption, particularly in the case of using data from a CRVS in this instance. When you use the household deaths module from a census, often this last assumption is actually violated. You can imagine a situation where the death of an elderly patriarch or matriarch of a household leads to the collapse of that entire household, the dissolution of that household. And therefore, in a household deaths module, it might well be the case that the deaths of particularly older women tends to result in the collapse and dissolution of a household. And so those deaths don't get reported in a household deaths module. That, of course, is far less of a concern if one uses, as we do here, the data from a civil registration vital statistics system to try and get a handle on the completeness of registration. There's no real reason why the completeness of reporting of deaths at all ages or for different sexes is going to be particularly problematic with respect to age. One of the data inputs which we required, other than the tabulations of the age structure in your from your census, to evaluate the completeness of the registration of adult deaths in the CRVS system, we require the numbers from that CRVS by age group, as we already discussed, as well as by sex, for the period between the two censuses. So you can imagine, for example, if you had two censuses conducted, the first on the 10th of October 2001, and the second one on the 10th of October 2011, you would need to either be able to extract the exact numbers of deaths by age at the time of death in those age groups and for the open age interval between those two precise dates, which would mean that you'd have to have data on your civil registration system, which would allow you to exactly pull out the deaths that occurred between the 10th of October 2001 and the 9th of October 2011. Or alternatively, if you don't have that, all you have in your CRVS system is the year in which those events occurred, you would then have to interpolate or prorate the deaths for 2001, so whatever total of deaths you have for 2001, to say what proportion of those deaths, on the assumption that deaths occurred equally over the year, are likely to have occurred between the 10th of October 2001 and the end of that year. To say, well, that's the portion of deaths which are in the intercensual period in 2001. And similarly for the deaths in 2011, which would be, you'd only want to include the fraction of deaths in 2011 from the beginning of that year through to the night before the census on the 9th of October 2011. But usually that is not too much of a burden to be able to extract from one's civil registration system. Either one has the exact dates of death and say, let's get out all the deaths which occurred exactly between the two censuses, or otherwise we can make a very simple proportional adjustment for the deaths in 2001 and the deaths in 2011 and include all the deaths in 2002, 2003, all the way through to 2010. So we would take those deaths from your CRVS, and we are going to require them as inputs into the GGB plus SEG type framework. There is one particular consideration in using data from a CRVS in this type of framework, and I want to illustrate that by means of an example. So let's imagine that your population and its residence by rural or urban areas varies by age. You can imagine a situation where, for example, older people might choose to leave urban areas and move back to rural areas around about retirement or for their old age. And if you imagine further that the completeness of your civil registration data varies significantly between urban and rural areas, well, then you are likely to violate that assumption violate the assumption that your completeness doesn't change or is constant by age. Because what's going to happen is that if people move from urban to rural areas to older ages, and completeness is worse in rural areas, and because by and large deaths tend to occur at older ages, it means that we will be underestimating our level of completeness in our civil registration data. And so that does need to be borne in mind, although there's no direct mechanical way of compensating for that feature. So the implementation of this GGB plus SEG approach, unfortunately, is best learned through experience and trial and error. And certainly in my learning, mostly through making mistakes rather than kind of endlessly getting it right. Like much of advanced demography, and these methods really do fall into the category of advanced demography, the implementation of these methods really does start to slide quite dramatically from being a science into being an art, in the sense that significant judgment is required to be able to apply these methods. But even if you personally are not a demographer or are not directly working with census data, this is something which perhaps other people in your country, other demographers in your National Statistical Agency might be able to assist you with, in terms of saying, let's ask them, relative to two recent censuses, ask them to apply the GGB plus SEG approach, and to let you know what the results are in terms of the implications for the completeness of adult mortality. The methods are described in very great detail, both mathematically and with worked examples in the tools for demographic estimation. I've provided the direct hyperlinks to both the GGB method, the generalized growth balance, and the synthetic extinct generations method in the slides here. And as always, the slides are available in PDF format on the Google Drive under Instructional Material. Given the complexity of these methods, really all I can hope to do is to give you a flavor of what might be possible to be achieved with this powerful approach, and very different approach to estimating the completeness of your civil registration data for adult mortality and adult deaths. And so I'm going to very briefly step you through the application of these two models to show you what we finally produce as an estimate of completeness by applying the GGB and SEG methods in tandem to South African data. And we're going to use data from our 2011 census, which was done in 2011. And what we had it was a census replacement survey, which was run in 2016, which was a very large scale. It was about a 2% sample of the entire population. And we're going to use that to try and get an estimate of the completeness of adult death registration in South Africa between 2011 and 2016. So let's move this across over here. Copies of this spreadsheet, as well as the reverse survival spreadsheet, are also under the instructional materials section of the Google Drive. So if you ever want to at least play with these spreadsheets, you can see the kinds of things which one needs to be able to do, or the kinds of outputs one can get from the application of these models. And the first thing which we're going to do is we're going to apply that growth balance model to get an estimate of the relative coverage between the two censuses. And here, what we have sorry, it was our 2011 census, sorry, 2001 census, not 2007 community survey, which is in our data here. And we're just going to say that we're going to use South Africa. The data are for males. We use the standard life table, which incorporates the impact of HIV and AIDS. We have a very dramatic HIV/AIDS epidemic in this country. And we need just to record the two census dates. The first census date was on the 10th of October, 2001. The second one was at the middle of February, 2007. And without going into any explanation of how the method works, if we go to the method sheet and look at what we need to put as the inputs over here, what we need are from our first census, our estimate of the population of males by age group, 0 to 4, 5 to 9, up to 85 and older from our first census. Our population in 5-year age groups at the time of the second inquiry, which was our community survey of 2007. We need an estimate of the number of deaths from our civil registration system between 2001 and 2007. These would be extracted from our civil registration system. If possible, also, you'd want an estimate of the number of net migrants by age. Between those two dates, so this is our best estimate of the number of migrants in our population into South Africa of males by age group between 2001 and 2007. The rest of the application of the generalized growth balance method is really fairly mechanical, but what we really want to get here is the cell marked here in red, which is the intercept of the line fitted to our estimates of the deaths from our data and our implied deaths from the synthetic cohorts. And the intercept of that line, you can see there's just below 0 there, is a measure of the relative completeness of the two censuses, the 2001 census relative to the 2007 community survey. In this case, you can see the number is incredibly close to 0. That's in fact not surprising, because both the census and the community survey ran a post-enumeration survey where they made great efforts to try and adjust the enumerated populations from each of those inquiries for their under-reporting and under-enumeration. And so this suggests that there's very limited differential under-enumeration between the two censuses. In actually applying the model, you would want to specify as many ages as possible to which you can get these data points to fit on a straight line. As you can see, they all fit quite neatly on a straight line there. You would want the residuals between your observed data points and your fitted line to be fairly small. You can see these are the order of 3 per thousand down to -4 per thousand. So very small residuals means it's a relatively good fit. But that requires, again, a level of expertise to ensure that you choose as many age groups as possible to fit this model to, and which you might want to ask for expert advice in applying to your own country. But crucially, what you want here is this estimate of relative completeness of the one census to the other. What we then do is we then take exactly the same input data and apply it to a synthetic extinct generation method version of a death distribution method. And so we would again use exactly the same inputs as before. It's just 4 simple tabulations of age, single by age groups, by 5-year age groups in the first census, in the second census or second inquiry, your estimate of your intercensual deaths, which is the same as from the generalized growth balance extracted from our civil registration system, our same estimates of the number of migrants. And all we really do is we put the estimates of the differential completeness between the two censuses into our synthetic extinct generation in that cell there. And it will then, the model will then directly estimate the completeness of your data. And what we see in this plot over here is exactly that estimate of completeness, either for each individual 5-year age group, which is the blue line, or for all ages above that age, which is the pink line. And what we can see here is that in general, certainly between about ages, ages 25 to about age 60, that pink line is almost level, which would suggest that our completeness of our adult mortality is largely consistent and coherent after that level, and it does tend to fall off slightly at older ages and fall off slightly at younger ages. But the crucial results are produced by the method directly, which are down here at the bottom, which suggests that this measure C, which is our measure of completeness, for ages 25 to 64, is around about 95%, and above all ages from 15 and older, our estimate of adult mortality registration completeness is about 91% from our civil registration system. And this is really an important result, because it uses a completely different approach to say, in that period between 2001 and 2007, using the information from 2 censuses, our estimate of the completeness of the civil registration system over that period, which would be roughly in the middle of 2004, the midpoint between those 2 censuses over there, was for ages 25 to 64 of the order of 94%, and for all ages over the age of all ages over the age of 15 is of the order of about 15%. All ages over the age of 15, the completeness of about 91%. And we can use this then to compare with our results, say, from application to alternative estimates. We could derive an estimate of completeness of those aged 25 to 64 from our civil registration data relative to South Africa's mid-year population estimates, or the population, the number of deaths aged 25 to 64 over that 5-year period, roughly 2000 to 2005 from another source. And so we can use this information to get a further indication as to whether we think the estimates of completeness are largely consistent and plausible. And certainly in this case, the answer is that yes, relative to everything else that we know about South Africa over this period, for certainly the kind of mid to early late adult ages, age 25 to 64, that estimate of completeness is not completely out of the ballpark of what we'd expect. Over age 15, that estimate of adult mortality completeness is also not entirely out of keeping with what we expect. And so I just want to flag this as an alternative way of kind of getting a handle on what you think might be the level of adult mortality completeness is. As I do say, and as I've said on the slide already, this is an area of demographic work which does require quite some experience in working and playing with these models and familiarizing yourself with exactly how they should best be implemented. But one hopes that within your country, there are demographers who have been exposed to these methods who might be able to assist you in producing those estimates of adult mortality completeness, which you might be able to then be able to use. So this brings us pretty much to the end of the instructional components of the training workshop. There's still obviously the practical sessions still to come. And kind of as we come to the end of the instructional part, I'd just like to say thank you. This has been a very amusing, very fun week with all of you. I look forward to working with you tomorrow during the practical sessions. There will be practical exercises uploaded in the next few hours onto the Google Drive if you want to get a head start on those things. We will be continuing tomorrow morning in the same fashion as we have, as we did do yesterday, with those instructional exercises, which you can either work on your own, or we can have one-on-one chats, which did seem to work reasonably well under the circumstances. I have also just put there at the bottom my email address if anyone wants to ever kind of query anything more which they which I've said, or going forward, they've got a question. There was a request yesterday that these also get, if there are questions, you might want to copy them through to the ESCAP civil registration inequality assessments team led by Petronamius, just so that they have a record and some insight as to the kinds of questions which are being asked. But at this point, I'd like to open up for any questions, comments on what has been covered in this morning's sessions, this afternoon sessions, this evening sessions for those of you in the far reaches of the Pacific. And to answer any more or resolve any outstanding questions and comments. But in the meantime, again, from the bottom of my heart, thank you very much.